slideshow. Okay. Good. So this is a rehearsal of our work. Okay. Okay. Hi everyone. This work that I'm presenting is a neural machine translation of clinical texts and empirical investigation into multilingual pre-trained language models and transfer learning. It is supposed to be in Manchester NLP Club, but it looks like many people are away since it's Valentine's Day, February 14th. And we have a GitHub page about our project. This work is a collaborative work with Serge, Gleb, Irina from Logos Global, Betty from Argentina, and Goran from NLP Group of Manchester. And it has been accepted to Frontiers in Digital Health. This is a screenshot from the journal page. And it is still under publishing processing for the full articles to be online soon. I will go through the overview or highlights firstly, and then go detail into the work. So the keywords is neural machine translation, NMT, and clinical text translation. Then another phrase you will see very often is multilingual pre-trained language models, MPLM. Then is small size versus large size MPLM. That is one of the main focuses of this work about their comparisons. Large language models, transfer learning, clinical knowledge transfer or transformation, and the Spanish-English translation, that is focus of the domain. For the motivations, clinical texts and documents contain a wealth of information and knowledge in the field of healthcare, and their processing using state-of-the-art language technology has become very important for building intelligent systems capable for supporting healthcare and providing greater social good. This processing includes creating language understanding models and translating resources into other languages to share domain-specific cross-lingual knowledge. Yeah, I heard some noise. Okay, microphone corridor. The method that we applied for this work is that we conduct investigations on clinical text machine translation by examining multilingual neural network models, especially using deep learning models to compare small versus extra large models. Furthermore, to address the issues of language resource imbalance, we also carry out experiments using a transfer learning methodology based on massive multilingual pre-trained language model. The outcome of our work is that the experiment results using 3 subtasks, including clinical case, clinical terminology, and ontological concepts, shows that our model achieved top-level performances in the 2022 Clean Span-EN shared task on Spanish-English clinical domain data. This is a shared task co-located with WMT, that is Workshop for Machine Translation, that has been around 20 years, that organize the flagship machine translation shared tasks and competitions. Furthermore, our expert-based human evaluations demonstrate that small-size pre-trained language model wins the clinical domain fine-tuning over other 2 extra large models with a very large margin. This finding has never been reported previously in the field, especially in clinical text translation. Finally, the transfer learning methods works very well in all experiment settings using the WMT 2021 Facebook model to accommodate a new Spanish language space that was not seen, that didn't see Spanish in the pre-training stage within this model itself. And this deserves further exploration for clinical knowledge transfer, such as investigation into broader languages. This will also cover some code switching outputs. So for the perspectives, our research findings can shed some light on domain-specific machine translation development, especially in clinical and healthcare fields. Further research projects can be carried out based on our work to improve healthcare text analytics and knowledge transfer. Our data, tools, and resources can be reached through the context in the GitHub page. You can also try the QR code to see what you can get. Let's see the main work we did. Firstly, for related work, natural language processing in clinical and healthcare domain has already been explored by some researchers, including disease status prediction, temporal expressions and event extraction, temporal relation and treatment modeling, the identification of patient information, and some review works. Then the other related work including machine translation for clinical setting, from statistical to neural models, using stochasticity terms, identify semantic concepts, extracting UMRS concepts, and simplify multi-stage workflow about report dictation using machine translation model. Regarding multilingual pre-trained language models, related to our work, we used Marine, that is 7 million parameters. WM21 Facebook model has 4.7 billion parameters, and the language left behind has 50+ billion parameters. There is this WMT biomedical shared task that we attended. It was from 2016, annually has been held so far. Regarding transfer learning, people have applied it to text classification, relation extraction, and low resource machine translation, which is related to ours. We have all these references to so far mentioned related works in the paper. In our work, the pipeline of investigation is that from left to right, we have small size versus large size multilingual pre-trained language model. The first two models, Marine and No Language Left Behind, cover Spanish and English in their pre-trained model. So we fine-tune it using our cleaned clinical data. So we got clinical Marine and clinical No Language Left Behind. The third model, WMT21 Facebook model, it did not have Spanish in the pre-trained model. So we carry out transfer learning to adapt to a new language in clinical domain. Then we carried out automatic evaluation using a broad range of metrics, followed by expert-based human evaluation and validation. Regarding small-sized marine NMT, if anyone is not familiar yet, it was trained using this pipeline that we draw. Pre-processing, shallow training, back translation, deep training, both directions, ensemble decoding, re-ranking of unbiased outputs, then automatic post-editing. For pre-processing, there include tokenization, true casing, pair encoding, etc. Shallow training is to teach mid-phase translation model to produce temporary target output for back translation. The deep training, firstly, they use 4 left-to-right models, which can be either RNN or transformer, then followed by right-to-left models in opposite direction. The RNN they use mostly is from Nemathers that developed in Edinburgh University. And for ensemble decoding, it generates the unbiased hypothesis translation of each source segment. that will be re-ranked using rescoring mechanisms. Finally, the automatic post-editing is to make the automatic translation better. Here, everyone probably have seen this picture. It's very important, the foundation of models, that is transformer, proposed by Google research team, Vaswani et al. In 2017. It is encoder-decoder model, including input embedding, position encoding, modified attention, feed-forward, both follow with normalization in the encoding part, and in decoding part, there's a mask modified attention to only pay attention to already generated tokens. Both our extra large language model, WMT21 model, and no language left behind are based on transformer model. But the difference, people might not know. For example, to increase the model capacity without making the extra large language model too slow for training, the 2021 physical model included a sparsely gated mixture of experts. They call it MOE models. This was inspired by the work from scaling paper in our, if you read our paper, there's this reference into the FML layer of the transformers. We'll show you this picture. In the left-hand side is a dense transformer, original proposed. In the right-hand side, you will see this MOE layer that is implemented inside this FFN layer. The MOE model will only pass a subset of model parameters into the next level, this way decreasing the computational cost. However, this dropout is done in a random manner. Another drawback of this model is that this structure design still needs language-specific training, such as English to other or other English that is restricted. Based on this work, it was published in Journal of Machine Learning Research, AI Research, if I'm not wrong. They call it M2, M100. And then there's next model, slightly different adaptation. That is the no language left behind model. It is designed as a conditional MOE routing layer inspired by 2021 work to ask the MOE model to decide which tokens to drop out based on how computationally intense or resource heavy they are to process, or based on their routing efficiency. So here there is a selection strategy, and this is achieved by binary gate, which assigns weight to dense FNN. You will see the difference between MOE gating and this new mechanism that is designed. So in summary, both WM21 physical model and NRB model share similar structures. The biggest difference being that the 21 physical model used language-specific constraint training. The 21 model we applied is WM21 dense, 24 wide, that is 14 languages, both direction. It has 4.7 billion parameters that you can download from this GitHub page we provided, and contains language pairs from English to Chinese, Czech, German, Hausa, Icelandic, Japanese, and Russian. However, the NLB model includes 200 plus languages and has 54 plus billion parameters. Because the computer restrictions that we have, we applied the distilled model of NLB that is 1.3 billion parameters. You can download from the link via our paper. Also here, you can pay attention that because this model did not have Spanish among its pre-trained language pairs, it is one best choice for us to investigate transfer learning technology to see if we can generate a new language domain using this pre-trained model. Regarding the experiments, we used medical bilingual corpus or MISPEN from 2018 work. It is a large corpus and it is also a messy corpus. So we carried out cleaning via Serge's team and in Localhost Global. Finally, we extracted 250K pairs of clean segments in Spanish, English, clinical domain, and we divided them into 9:1 ratio for training and development purpose. This was, if I didn't remember wrong, it was introduced by error, but it led to interesting findings. Parameter settings regarding marine is listed here. And for NLB fine-tuning, this is the parameter we applied. For WMT 2021 model, it is same set of parameter except for the batch size. We set only 2 because we will get out of memory error if it's larger than 2. For testing, there's 3 tasks. First is English to Spanish, including 202 clinical case reports. Include each report have multiple sentences. Task 2 is Spanish to English, that is 19K clinical terms, and that is short phrases. And then task 3 is English to Spanish direction again with 2000 ontological concepts from biomedical ontology. So these 3 testing sites actually are relatively large, especially task 1 and 2. This setting was because the organizers want to test the generalization or generalizability of submitted systems. If the model is really good or either it won by chance. I remember research complained at that time, like the test size is so big if the organizer are using submission team as free labor, if I didn't remember wrong. So for task 1, 2, 3, we have automatic evaluation scores using Sacred Blue, Meter, Comet, Blue, and Rouge score. Among these metrics, Sacred Blue was chosen by the shared task organizer as the primary metric. So we also ranked the system according to Sacred Blue. And Comet is the only metric using embedding space compared to other lexical level metrics. In this evaluation output, you can see clinical marine, that's the smallest model, produced the highest Sacred Blue score on sentence level clinical case evaluation, which was quite surprising to us. And then clinical term and concept translation. These 3 models have similar scores. And marine was lower than NLRB, but not much. So this score is a bit confusing to us. In task 1, marine was best at sentence level. In task 2, at term level, it had around 2 points lower. And task 3, it has around 2 points lower. That's also one of the reasons we plan to carry out a human expert-based evaluation to see how exactly this system differentiates with each other. A brief summary here, I also briefly mentioned. A much smaller clinical marine model had most of the highest scores across 3 tasks, indicated in italic case, which was surprising to us. The transfer learning model has a certain score gap to an RB on task 1, but it catches up in task 2 and 3, especially 3. You can see it has only 1 point difference. Also in other scores, it's almost similar with a meter score. That means the transfer learning model is powerful. Thirdly, also importantly, we say that there are issues with automatic metric. This includes the confidence level of score difference or significant tests, such as the very closely related scores for task 1 and the first 2 Wonder models. In addition, the Wonder model changed across task 2 and 3. So we think automatic evaluation is not what we want in the end. And we also observed there are 4% of Russian tokens in the transfer learning model that we will discuss more in the human evaluation. So this one is what we want to compare with other team. Here you can see we use clinical marine or small model compare with Optium, Huawei, and marine actually won Optium using the official evaluation metric Sacred Blue. Huawei actually didn't win the first team, and very close to clinical marine, that is a very small model. And in meter score, actually the small model also won other 2 metrics, also root score. So these metrics do not really agree with each other, but it says something. We summarize it here. Compared to other teams, much smaller marine clinical marine model actually has its advantage. And then Optium and Huawei is the 2 teams we compared, where Optium attended all 3 subtasks, so we can list them on all 3. However, Huawei only attended task 2 on clinical terminology, so we cannot see their other shared task output. Firstly, the much smaller marine models win metrics on each task. Then Optium use their in-house clinical data as extra training resource in addition to WMT offered training site. However, Marine only used 250 training sets. We extracted that from the official training data. This is also called constrained fine-tuning versus unconstrained fine-tuning. Huawei's model only won 1 metric, that's Comet, out of 5 metrics of task 2. That says actually Huawei's performance on this task is not much better than other teams, even though they have greater online resources and especially computational support. You can see from here. So for human evaluation that we have mentioned a couple of times, the need to achieve both quantitative and qualitative human evaluation, we developed a human-centric experts-based post-editing quality evaluation metric called HOPE, and that was published in 2022 in RREC by Serge and myself. It's also called LogiPAM because it was invented by Logos Global. The HOPE evaluation metric has 8 predefined error types according to statistical analysis from historical data. And each error type has corresponding different levels of penalty points from minor to medium to severe errors according to their severity level. The sentence and system level HOPE scores is a comprehensive score reflecting the overall quality of machine translation output. This is a link to the HOPE metric paper. For our human evaluation setup, we recruited 5 human evaluators that have the backgrounds in professional translation, linguistics, and biomedical research. We took all of the test set from task 1, that is clinical case sentence level report, since this is the only site including full sentence. For other 2 tasks, for terminology and ontology level translation, we think the machine translation engine can produce relatively good outcome even without model. For example, we can use a very broadly bilingual dictionary or terminology dictionary. We prepared 100 strings for each site and send them into all the 5 sites to professional evaluators, so there are no confusion. Each of them was given 3 files for evaluation from different engines, and instructions were given on both the online perfectionist tool that is developed by Locus Global as well, that was used for evaluation and on the Hope Matrix. Then we also asked the strict reviewer or the evaluator to validate the work of other evaluators. There was a question raised by the reviewer about the strict reviewer. So the strict reviewer is the one who made a better distinction between all 3 evaluated models, while the less strict reviewers sometimes give similar scores to these models without picking their errors rigidly or rigorously. This chart shows the comparison between automatic evaluation and human evaluation score. Here we can see the average score of automatic evaluation meter and root is 63, 62, 58. Without much gap is right between the first 2 models. But using Hope metric, we can see that the first model, Marine, achieved 80 score, the second is 76, and third one, transferred model, was 69. This is a much bigger margin gap compared to automatic evaluation metric. Straightforwardly, we can also see from this chart the advantage of human evaluation use Hope metric compare with automatic metrics. This is a breakdown of human evaluators from evaluator 1 to 5. From this breakdown, we also calculated the confidence intervals of 3 models and where it stays. We also carry out the error analysis, also as requested by our strict reviewers from Frontiers. In addition to Hope analytics with predefined errors, we also have sampled output that we looked into, and we found some typical categories that we can clarify them into literal translation, oral versus written language translation, inconsistency, inaccuracy of terms, hallucination or made-up words from these neural models, and gender-related errors, such as feminine versus masculine translation. We listed examples of each of these errors in our paper. For example, this is sentence level translation sample. This is terminology translation. And this is ontology translation. For example, in the case that is sentence translation, for the first 2 sentences from clinical WM21 model, they are more written Spanish than an RB model, which produce more oral Spanish. And then you can see other examples, including gender, hallucination, literal translation. errors. So one thing we mentioned before is that we had 4% of Russian tokens observed in the English to Spanish translation output from transfer learned model, the clinical WMT21 model. However, when we looked at the sample output, the 4% of Russian tokens, they are meaningful tokens, not nonsense tokens. For example, in our case example, this Russian token, they have actually meaning. You can see it, for example, line 4 in case. Here you will see Russian tokens, but it's meaningful tokens, not nonsense. That means that when the model did not know what the spicy term should be, they kept the Russian token as the output instead of using the accurate Spanish one. So in conclusion, to boost the knowledge transfer for digital healthcare and get the most knowledge out of available clinical resources, we explored the state-of-art neural language models regarding their performance in clinical machine translation. We investigate both smaller multilingual pre-trained language model, Marine, that is from Helsinki NLP group, in comparison to two extra large multilingual pre-trained language model from Facebook or Meta AI, nowadays called. We also investigated the transfer learning possibility in clinical domain translation using this Facebook model. We carried out the data cleaning. That was a very important part of this work. And finally, in the clinical domain, we evaluate work using both automatic evaluation metrics and human expert-based evaluation using Hopper framework. Our two findings that we want to point out is that the bigger size of model does not mean that the quality is better in our situations. The second point is that automatic metrics deliver an illusion of measurements, so human evaluation is always needed. We really thank our human evaluators who did their hard work by volunteering to do this annotation. We also thank Christina for assisting double-checking the sample human evaluation. And me and Goran are grateful to the grant support from HIPS and MASK that was funded in UK. This is our GitHub page that you can have a scan, see what you'll get out of this work. Okay, so that's the presentation. Now I will stop recording. I'll pause it.